everyone. Thank you for the intro and thank you for attending the session this morning. It's the first session, so I really appreciate everyone coming. I'm Alex from QuantStamp, and together with my colleague Valerian, we looked at how the bytecode chaos can be managed through introduction of EVM Object Format, or EOF. And so what is EOF and why? So there was actually a really nice talk by Dano Ferrin on Tuesday, which dives deeper into the motivation, and I highly recommend watching that when you get a chance. I'll just briefly mention what this is about. So EOF is EVM Object Format. It's a new format of the EVM bytecode and usually formats have special magic markers, right? So in this case, it's EF00. So if the bytecode starts with those characters, those bytes, it means that it's EOF code. It was originally considered for the Pectra upgrade, and that's when Valerian and I first looked at it. Then it got postponed, so potentially it will be part of one of the upgrades after that. But apart from the technical readiness, are we actually ready for this upgrade? Because the questions to ask here is, do we understand it well enough? What does it do, right? Is the tooling ready? What are the upside and downside of this new format? And how's the security side looking? So all these questions we were trying to answer in this talk. And why? Well, currently any bytecode can be deployed as a smart contract. There is no predefined metastructure, no well-defined versioning. So it's basically maybe some semantics can change over hard forks, or new opcodes can appear with the new hard forks of the EVM. But there was no indication of the versioning that is actually part of the bytecode. And there is no thorough deploy time validation of the code, so which makes a lot of other things tricky. And overall we have the following issues, right? So it's difficult to add and deprecate features, as many of us have experienced being the devs. And it's hard to analyze the code, and also it's a little bit difficult for the compilers. And also, it's hard to fully solve any long-lasting, omissions in the original EVM, because as Dana was mentioning on the talk on Tuesday, it's either you have to just keep making small tweaks, or you have to just break everything at once and just make it right. The solution there is we add structure, versioning, and EVM is made better in that new version, while the legacy version would continue to live on. And so EOF is actually quite a complex upgrade. There is, on the right side, you see quite a few EIPs that go with it. And my colleague there tried to draw a diagram of how this is all pieced together, and with some arrows that signify some of the interactions between EOF and legacy. We do not have time to look at all of them, so I will just try to give a bit of highlights of those items that I've highlighted on the slide. And we'll give some code examples as well. So let's get to it. Well, on the left side, you see basically a toy example. This is a very, very simplistic example because we just wanted something simple to go with, to just showcase the differences between the legacy VM and the new EOF format. On the Solidity side, we just have an infinite loop contract, which pretty much just loops forever until it runs out of gas. This is how below you see how it could be represented as a bytecode. This is a very rough manual translation there. The actual bytecode would be much larger because there will be additional checks included by the compiler. So what we have here is basically jump test instruction, which is 5B, and then followed by push 1 with 0x00, which is the location to jump to, and then finally the actual jump command. So it's basically you tell where the jump destination is, which is in this case just 0x00, and then you push that value into the stack, and then you jump to that location. So it's pretty much the infinite loop. That's how it's intended for this example. Now let's look at EOF. Here we have a whole bunch of other things. We now see the structure, right? There is the header, and there is the body. In the header, we have EOF magic, which we've already seen on the previous slide, which is followed by the version, version 1 in this case. Then it describes the sections. In this case, we have the types section. Types is indicated as 0, 1, and the length of that type section is 4 bytes. Same with the code section. We have one code section, which is also 4 bytes long. And finally, there is the data section, and we will not dive deeper into that. We just kind of omitted that completely. So there is no data section. Its length is 0. That's as far as the header goes. So in the body, there are 2 subsections. One is the types, and another one is code. So in the types section, what's described is the number of inputs, number of stack elements, or in this case, there is a special special byte sequence, just 0x80, if there are none, and the maximum stack height, which is 2. So the way I think of this type section, from my perspective, it's almost like the signature of a function, but applies to the whole contract in this case. And finally, then we have the body section, and that is where we would have placed the bytecode from the left-hand side. That would have been the correct place for it. But as we see on the next slide, this bytecode is actually no longer valid in the EOF world. Okay, so this is our simple toy example that we'll go with. So what is wrong about that bytecode that is highlighted in red? Well, the thing is, in EOF, static relative jumps replace the conventional dynamic jumps. And yeah, so in the legacy EVM, jumps are dynamic, which requires so-called destination code analysis, since it is not clear beforehand whether the code at the destination is even a executable or a valid code. So that's why the analysis had to be done dynamically. And to simplify that, we had to have this jump test instruction that we saw earlier to highlight that this is one of the valid destinations for the jump. Yeah. So yeah, as we see here in our toy example, that's how the toy example will be translated from the legacy bytecode into the EOF bytecode, right? So on the in the middle here we see jump test, push 1, and jump. On the right side, we replace that absolute jump with a relative jump, and just for the purpose of this example, we say, well, how about we just jump to -1, which is just going back. So that way we kind of get the infinite loop. Okay. How about deployment of smart contracts? Well, in the legacy VM, what we already know, we have to use the create instructions, and there is the concept of init code, which gets executed just once, and this will pretty much place the bytecode onto the permanent storage. So here on the left side, you see the init code, which looks fairly standard. It's basically just pretty much highlighting the the sections of the memory where the bytecode is and storing it, and then there is the final return statement at the end. And the actual code is pretty much at the end here. So it's the same bytecode as we've seen on the previous slide. Well, now how about EOF? Well, interestingly, EOF init code is also on itself a EOF smart contract, so EOF bytecode. So what we have here is we have the header and the body. But the interesting thing here is that there is a so-called subcontainer. And the subcontainer is pretty much the bytecode that we've seen on the previous slide of EOF. So you see at the very, very bottom there, it says subcontainer, and it's exactly like we had on the previous slide. So pretty much what you see on the right side here, that's what is at the bottom of this slide. And if we go over this a little bit, we have also all these different sections. And in the header, we see that there is a definition of subcontainer, which is 03, and it's 22 bytes long. And by the way, Foundry has this nice command now called cast decode EOF. So if we run the bytecode through that command, here is the visualization that Foundry gives us. It is quite neat, pretty much another way of looking, of visualizing the bytecode. And what about functions? Well, it turns out that functions can also be self-contained and encapsulated within EOF as different code sections. For example, in this example, we have just a subroutine which doesn't do anything, just returns the input back to the caller. And in the legacy code, that's how we would probably code it by hand. And in the EOF, what we have is we have the callf and the readf instructions now, which could allow us to pretty much do the function calls within the same EOF structure, just using different code subsections here. So we have code section 1 and code section 2 here. And the standard EIP 3670 defines how code validation is to be done. Then, usually it involves basically just validating whether all the instructions are valid. And for example, self-destruct and all the legacy instructions will be deprecated. And so this jump test analysis is no longer necessary there because all the jumps are replaced with relative jumps. So this should make things easier. Well, I guess the question is, what about interactions between the legacy and the EOF contracts? So which rules would apply there? Well, we just glanced at it, and it seems like some interactions are allowed and some are not allowed. For example, create2 will fail if you try to deploy a bytecode starting with 0xEF, which is actually already a part of the EVM as of now. Can EOF contract deploy a legacy contract? No, so this is not valid. Can an EOF contract call a legacy contract? Yes, if you use xcall and xstatic call, it is allowed. In case of delegate call, or I guess replacement of delegate call, this is not allowed. Can legacy code call an EOF contract? Yes, it is possible, and the intention there is that the existing proxy contracts can be upgraded to use the EOF implementations. And also a note there that EOF must not be enabled on chains where the EF00 prefixed bytecodes are not valid EOF. So that's already taken care of. Another modification is call instructions got revamped to remove the so-called gas observability, because it has been an issue before. And as of the EOF upgrade, at least in that EOF version, the caller will no longer have control over the amount of gas that is passed as a part of the function call. So that was like one of the notable updates. And certain other rules were kept, for example, the 63/64th rule and also max call depth, even though it was considered for removal. And a few other modifications as well. Well, how about support and implementation? To our knowledge, we are not core devs. We just like pretty much we are looking at publicly available sources. So far, it seems like it's still in the works. It's implemented in some of the clients, but in some other clients, it is not fully implemented, including Geth and SEA. So we didn't try as much playing around with these tools yet. But I think that this will be a completely different story later. And while checking for materials for this talk, we found a few interesting tools, which include the fuzzer, include some code performance benchmark, and also bytecode parsers, EOF bytecode parsers. And yeah, and some other useful sources. There are no URLs here, but let me know if you're interested. I can just share the whole slide with you with all the references. Yeah, and interestingly, we found a few performance analysis of the new format. So the Build-Bear labs have conducted some tests, and the results are here, and they are available at this URL as the source. So the takeaway there is that the execution time is actually also about 15% faster. Apart from all these other, we see some reductions in the init code size, in deployed code size, and also the gas usage for deployment, which is quite interesting. So how about the security aspect? So yeah, we had we looked and tried to find more data on this, but it seems like so far these are the few points that we were able to find. So one is removal of jump test analysis, which has its own positive implications on analysis of the bytecode. Stack operations have been revised. This upgrade is not EOF specific, and I noticed that there is another talk on EOF later today in this room, which potentially would dive deeper into this topic. Yeah, and static jumps, as we've already mentioned, and also the revision of gas observability. So these are potential indirect benefits on the security. And for the stack operations revision aspect, it can prevent from this stack to deep issue that previously sometimes required writing your code and potentially make it simpler or make it more complicated depending on the code that you have. And what are the drawbacks and risks? Well, I think it's, in my opinion, it's mostly about complexity. So we have so many new opcodes introduced. All of them need to be tested, and you also have 16 legacy opcodes that continue to exist, and you have 152 shared opcodes that will be existing in both versions. And yeah, I think that would be good to actually have more publicly known security analysis of this change. But I'm sure this will appear since it's still a work in progress. So I think that this should be good. Well, and so in conclusion, basically we just tried to learn a little bit more about EOF and try to convey our understanding, our perspective on this. And yeah, of course, all of this is subject to change, and also we are not core devs, so it's totally possible that we got certain inaccuracies in our understanding. But nevertheless, I think that goal is to basically learn more about it and have the community a little bit more engaged in this topic. Yeah, and so EOF should manage the bytecode chaos by versioning structure, relative jumps, and better stack management and deploy time validation. And yeah, EOF is seen as more like an investment in the future. I think the benefits will be clearer in the long term. That's it from my side. Thank you.
Thank you, Alex. That was a very interesting talk. So we have quite a few questions. If anyone else wants to ask a question, please scan the QR code there. So let's start with the most popular one. So is code size an important concern? And does EOF help reduce code size? What about performance?
Yeah, so we personally did not do the analysis on that front, but we saw other teams did that. So for example, that slide that I had with Build Bear, labs that did this analysis, and they did see the reduction in the code size and also improvement to performance. I think performance is definitely one of the aspects. So yeah, I think that this is looking promising on that front, but it will be clearer as we have more, I guess, more people look into this topic.
Great. So what's the Viper's progress towards EOF? Is it going to be supported?
To be honest, I do not know, but maybe if somebody who actually works in that would be good.
Okay, so what's the reason for relative jumps instead of directly indexing of bytes in the code array?
Yeah, so relative jumps, in my understanding, have certain benefits. Because it allows you to actually write the code that is more or less self-contained and encapsulated. So you don't always have, maybe you don't always care the absolute location of the code, but you pretty much can reference other sections of the code and also the code within the code section in a relative manner. So I think that this provides this type of benefit, in my opinion.
Great. So I guess there is already a PR for Geth, which is good news. I really like the next question. What are the arguments against EOF?
Well, the main argument we've seen when looked at this talk is just the complexity, right? Because it's a very complex upgrade. There are so many things. It kind of makes sense because from Dano's talk on Tuesday, it's basically been pretty much an effort to try to make many changes all at once, because you cannot just do all this kind of piecemealing of the changes. You cannot just simply do it without breaking other things. So it makes sense to kind of have one major complex upgrade. And if you have the versioning along with it, then you can pretty much have that done in a non-breaking manner while continuing to have the legacy code supported. So yeah, I think the complexity is probably like one aspect.
Mm-hmm. So for apps which invoke transactions with an arbitrary gas limit, will that param simply be ignored post-EOF?
Yeah, so my understanding is that maybe it will not even be allowed to pass it, but I do not know the details of how it's going to look like from the developer's perspective. But yes, definitely it seems like the concept of gas observability is to be deprecated, so it will be probably not possible to work with these low-level concepts as gas.
Mm-hmm. So the next question is about legacy opcodes, and I guess if they are going to be removed from existing EVM implementations, which...
Yeah, my understanding is that all the legacy bytecodes would still continue to be supported, right? So you cannot simply just completely remove it. In the EOF format, if your bytecode starts with EF00, that's a different story, right? So basically, you would have better control over which opcodes will be part of that new upgrade. So it's a different, pretty much, format. Yes, from what I recall from my slides, there will be some legacy opcodes that are completely removed or replaced with the counterparts for the removal, for example, self-destruct, right? So finally, you can actually just Well, I guess removal here means just not including it in EOF. So that's yes.
Great. And what happens, because we don't have that much time, what happens if there is a legacy opcode in EOF? It's going to be rejected or it's going to be in a runtime error?
Yeah, so there is basically, yeah, we looked at some interactions of EOF and legacy bytecodes, and some interactions are simply not even allowed. So for example, you cannot deploy EOF, or you cannot deploy a legacy contract from a EOF contract, and vice versa. So it's kind of like they draw the line somewhere where you only can go in one direction, and there is some disjoint sets of interactions that are possible.
Great. Thank you again. It was an amazing presentation. Let's thank Alex one more time.
Thank you so much.